4 additional topics in probability and counting. Um, Thinking about probability, it's important to think about whether or not you have independence or a dependent situation. So let's look at these notes. Like if we are thinking about probability, it's nice to know our numerator, our number of ways the event of interest occurs, over our denominator, the total number of ways in the sample space or data set, depending on if we're doing theoretical or empirical probability. But when we're finding the probability of picking multiple items and order does not matter, we must consider all the ways that the order could have been reordered for the items. So let's think about these examples and how they're a little bit different for this situation. Okay, we have a family and it's going to have 4 children. We want the probability that the family has 3 boys and 1 girl given a family of 4 children. So we know we're only looking at families with 4 children, and we want the probability that you're going to get a boy, a boy, a boy, and a girl in that family. So 4 events happening 4 times that they're going to the hospital to have this child. 4 parentheses set up to show these events that are happening one after another. And when you go into the hospital, to get that boy that you're interested in, there's 1 out of 2 ways that can happen. And because this is independent, because the next time you go into the hospital, you have the same boy and girl situation that can happen. There's a replacement where you can have that same gender happen over again. So that's why we're going to have our probabilities going to stay the same, and it's going to continue to do that as we pick our next boy and then our girl. So the probability of getting a boy, 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 girl was 1 out of 16. Now, go back to the problem and say, but order does not matter. They didn't say it had to be a boy first and then another boy, boy, and then the girl had to be the youngest. We could have had a family of boy, 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 girl, but we could have had that girl as the 3rd child or the 2nd child, if I'm looking at the sample space, could have been any of those ways. So there's actually 4 ways that you could have had 3 boys and 1 girl given a family of 4 children. So let's take our 1/16 and let's multiply it by 4. And so the probability of 3 boys and 1 girl in any order, it looks like it's a quarter or 0.25. Now, obviously this next problem is going to be slightly different. So what's different about this problem where you have a jury consisting of 5 men and 7 women on the jury, and you want to go out and you're still taking 4 people, but this time you want 3 men and 1 woman. It looks really, really similar. So we're going to go out there and pick a man, another man, and then a woman. And so again, it's 4 events happening, picking these people out of the group, but it's not half for a boy or a girl. It's we've got to get a man in this first parenthesis, and there are 5 of them out of 5 out of 12 in all. When we take the next man, what's different about the probability is it's a dependent situation where we had no replacement. We weren't putting that man back into the pool and potentially picking him again. We're going to pick a different man and have him be on this group. So now we're 4 out of 11, and this continues the process as we take our next man, and then we need our one woman right here. And I get my probability. But just like before, we could have our situation with the woman being picked third, or the woman was picked second, or the woman was picked first, and then just men. So again, 4 ways to accomplish this situation. All of these probabilities, the probabilities of each one of these situations is exactly the same. It's just order is commutative for multiplication, or it doesn't really matter, so we can do that. So the probability of getting 3 men and 1 woman will be 0.035353 times 4, or 0.141. So slightly different situation. So it's going to be really important if we can identify if a problem has replacement, no replacement, or has replacement. We can determine if it's a dependent or an independent situation, and that's going to help us with our probability. So this chapter has all kinds of formulas that look very exciting and complicated. The first thing is we have permutations. That's when the order matters. Oops, order matters. So if I really wanted that woman to be picked last, but in combinations, the order doesn't matter. And there's some great formulas in statistics that help us find permutations and combinations. Now, the first thing is if we have like objects, this is a great way to help us figure out a distinguishable permutation. Like, for example, in our situation where we had a man, 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 and woman. So we were picking and 4 items, and we saw that we had 3 of them were men and 1 of them was a woman. So I can put that into this formula right here with my 4 factorial over my first group being the men, 3 factorial, and then I only have 1 more group, and that's 1 factorial. Okay, what does a factorial mean? 4 factorial is going to mean 4 times 3 times 2 times 1 over, now we have a 3 factorial, maybe I should, we have a 3 factorial, that's, let me write the, times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. So if we look at our situation right here, we can see that there's going to be some canceling with our fractions, as if our denominator has our 3 times 2 times 1, those are all going to go away. And 1 factorial, that's just a 1. So that's verifying that 4 ways that we got on the first page. Okay, so some properties of factorials. Here's, letting us know that factorials, it's not, really loud number. It's multiplying all the way down to 1, that number and every number after it, like, for example, in this situation here and in this situation here. And that's interesting. 0 factorial is actually equal to 1. So that's great. Also, 1 factorial is equal to 1. Kind of interesting. 2 to the 0 is equal to 1. 0 factorial, they're all equal to 1. Those are just some examples. Okay, so if we have order does not matter, we have NPR where the order matters. That's when you have no replacement. you have n distinct objects. You're going to take r of them at a time. And so then we can see our formula, n factorial over n minus r, whatever that difference is, factorial. So how many ways can team first, second, third, and fourth places occur if there were 10 teams in a tournament? So there are 10 teams, and I want to pick 4 permutations for this. 10 factorial over, let's see, what is 10 minus 4 factorial? So that's going to be 10 factorial over 6 factorial. I like to think of that in terms of the 6 to 1 is canceling. So I'm going to end up with 10 times 9 times 8 times 7, which is going to be 5,040 ways. And that's if you need that first place position is first. So it's important. If you came in first, that's an important thing. So order did matter. And we saw that there was no replacement because when somebody crossed the finish line, they didn't go back and try to cross it again. Okay, so then what about combinations? So combinations is when your order doesn't matter. So an ABC is going to be considered exactly the same as a CBA because we don't really care about the order. So what happens is down here in our formula, it looks a lot like the permutations formula, but what this does is it basically divides by the ways you could have reordered your situation. And you may see this in the SATs. They might write it like that. And that's also meaning if you want to use similar notation to the permutations, you can write your combinations like that. So if we have an example of how many ways can 5 hearts be picked out of a standard deck of 52 cards, 52 cards in the deck, there are 13 hearts in that deck. That's a standard deck of cards. And so when we take out a card, we are not going to put it back. So it's no replacement. And the order is not going to matter because I can reorder them in my hand. I don't care what order I got my hearts. I just want to get hearts. So when I'm reordering them, so I'm going to have 52 cards, of which I will take let's see, 52 cards in the deck, and I'm going to take 5 cards. This would be taking cards out of all the cards. So that would be the total number of ways. And when I put that in 52, I put that into the calculator. You can find this setup in the calculator. You can find it under Math Prob that's in there. Just have to remember to put the 52 in first. Under Math Prob in your TI 84, you can find that. So if I do that, I get 25960 ways. But then I want to think about how I'm going to pick my hearts. There are 13 hearts in the deck, and I need to pick 5 of them. So let's see, how many ways can I pick those? I can have 13. I'm going to write it a different way just to experiment around. 13 hearts, and I've got 13 minus 5 factorial and then 5 factorial. So I end up with 13 factorial over 8 factorial, 5 factorial, and see if you can punch that correctly into the calculator, or use your math prob to get 1,287. You have to make sure that you've actually divided by that 5 factorial. And by the way, the factorial, you can find that in the calculator under math prob as well. So the probability of getting 5 hearts from the deck, there were 1,287 ways to get those cards, those out of the hearts, and there were 2, 5, 9, 8, 9, 6, 0 ways in all, giving us a probability, a very, very small probability of 4.95 times 10 to the negative 4. Pretty unusual to happen. So when you're trying to do these problems, and I've got lots of problems here, you don't really have to watch all of them, but definitely look through some of them, see how many you can do. We have to be asking ourselves if there's replacement, if there's like objects, does the order matter? Because that's going to help us decide if there's no replacement. It's going to help us decide if we have a permutation situation or a combination situation. And so those are the questions you need to ask yourself when you're doing these problems on the next pages. Okay, so in this problem, we want to take these letters and see if we just throw them down. Like, are we going to be able to get the word Mississippi spelled if we just throw them down? What's the probability of that happening? Picking them out of a hat. We have how many letters in all? There are, let's see, there are 11 letters in this word. And we are thinking about the order mattering, but we have distinguishable items that we're going to see how many ways we can order. We can't really tell the P's, which P from another P, we can't really tell. So that's why we have to think of them as we're going to use a distinguishable permutations to see if we can figure out how many ways we can reorder this. So how many ways can we reorder 11 items? Well, there was 1 M, 4 I's, 4 S's, and 2 P's. So there are 34,650 ways you could reorder these letters. What's the probability of spelling Mississippi in exactly that order? There's only one way to do that out of all the ways those letters could be reordered. So really small probability of this happening, very, very small. Oops, move that so you can see that. So that was a distinguishable permutations case. This time we have 8 types of donuts in the bakery. What is the probability that chocolate glazed, a maple glazed, and a plain are selected when we're picking 3 donuts? So it looks to me like there are 8 types of donuts out there. We want to pick 3. So we want to pick 3, and we want the order. Once we've picked one of the types, we're not going to go back in and be able to pick that same type again. So we have one of each donut. So there's no replacement for these donuts. So if we're going to try to pick from these three, we want the three types. We want the three types. Then we want to be able to pick from these donuts the three that we want. There's only one way to do that. But if we have the 8 types that we're picking from, and we're going to take our 3 that we want, and we're looking at the total number of ways, well, then there's 8 factorial over 8 minus 3 factorial, 3 factorial. There's 8 factorial over 5 factorial, 3 factorial. There's 56 ways to do that. So, probability of picking the 3 donuts that we want. I think I'm probably saying donuts wrong, but hey, it's okay. Nobody's here to complain. And there's a probability of that happening. Okay, so if we have the next one, probability of selecting a passcode. So that to me is an order matters situation. But we know that we are going to have a 3-digit code and no digit is going to be repeated. So if that is telling me that there's no replacement. So let's think about how many, well, there's only going to be one code that is our code. There's only going to be one code that does that. But if there are 10 digits, because it's 0, 1, 2, ... all the way to 9, those are our digits. There are 10 digits, including 0. Then we can pick 10p3 and we can see that we've got 10 factorial over 7 factorial. Think about that. If you're picking 3 things, 3 events happening, in that first one there's 10 ways, and next time it's dependent, so it's going down. This is the system we were using before, and it still works with this situation, watching for dependence or independence. So there are 720 ways to have a passcode, but only one of them, our code, only one of these passcodes is right. So 1 out of 720, and that would be a probability of 0.00139. Find the probability of selecting the passcode correctly if we know the code is a 3 digits and the digits can be repeated. So yes, replacement. So we are not going to be able to use NPR. We're not going to be able to use NCR. Those things don't apply in this situation because we have replacement, so that we have to have things coming back in independence. That gives us some independence. So we'll have to think through our code. Well, the probability of getting our code, again, there's still only one way to do that. But in the denominator, how many ways can we get the code? So there's, thinking back to my parentheses, that the first code could be 10 ways to do that. And if we're independent, There's still 10 ways for the next code. I can repick those digits and do all that. So that probability of selecting our code in that situation, which is a little bit smaller than what we saw if we're not going to let the digits be repeated. Okay, food manufacturer, the next page. Food manufacturer is analyzing a sample of 400 kernels for the presence of a toxin. In this sample, there are 10 kernels that are bad, and because they're high in toxin, and you're going to select 3 kernels from this situation. So 2 ways to think about this. There are 400 kernels. There are 10 bad kernels and 390 good kernels. We have no replacement. So I'm going to be able to use either NPR or NCR, but is it permutations or is it combinations? Let's think. Does it matter what order I get those toxin kernels? No. So no order to this. So that is going to be a combinations situation. And so we want to get our things. So if we have the probability that we have 1 bad and we need 2 good, and we're going to pick them using combinations. Well, I have to pick a bad one in the top. There are 10 bad to pick from, and I don't care what order I do them in, but I need 1 of them. These notations, they can be written right next to each other to show that we're going to be multiplying, and I need to pick 2 good ones out of that 390. But my total number of ways of this happening, there are 400 kernels, and I need to just see how many ways, the total number of ways of getting 3. So the probability of getting bad, once you punch all these numbers in, first one times the second one times the next one, you get 0.0717. Now, another way to think of this is, okay, I want a bad, I want a good, and a good. So I need to get a bad kernel. I need to get a good kernel. Notice how I'm decreasing my denominator because it's a dependent situation. Now I'm going to have to decrease my numerator because it's a dependent situation. And so then I get, well, of course, I don't have that number written down. Let's see here. I get I get 0.02388, but there are 3 ways to do this. So when I take that number and multiply it by 3, remember you could have a girl, boy, girl, a girl, girl, boy, but of course we're talking about good and bad kernels, but hey, it came out the same. So that's great. So there's more than one way to do these problems, to think about them. The chapter 3.4 really focuses on those combination and permutation notations. So see that in your textbook, but you can think about it in the ways we were doing before too. Okay, this problem. 400 kernels again, same exact situation. We've got our 400 kernels, we've got 10 bad, we've got 390 good. Same situation, but this time we want at least 1 has high level of toxin, so that at least one bad is what we want. And again, with 3 kernels being taken. So there are many ways to have, we could have 1 bad, we could have 2 bad, we could have all 3 bad. The complement of all these things, and of course there'd be 3 ways to do that, and there'd be multiple ways to do all these things. We're going to end up with 8 ways in all, but there's one way to be all good. So probability at least 1 bad will be 1 minus probability no bad. So let's find out the probability of all good, which we can do with the notation from this chapter that we want no bad ones. That's going to be a 1, so really I don't even have to write that. But I want to get 390C. I want to take 3, all of them being good, out of 400C3. Okay, probability of that happening. So, probability at least 1 bad is 1 minus the probability all good, and I get 0.0733 if I round it to 3 significant digits. And this section is just a lot of similar problems, tackling them, that way, tackling them the other way, where you're looking at different techniques for finding the probability. This one being, you want 2 letters, then you want to have 3 digits, then you want 2 letters, and you are trying to look for the probability of receiving a license plate with the number 666 on it. So you have got, do we have replacement? Yes, the numbers are going back in, so that means we cannot use the combinations, we cannot use the permutations. Those things are not available to us, but we're going to find the probability of getting a 666 on our license plate and think about how many ways can you get this. Let's see, 2 letters followed by 3 numbers followed by 2 letters. So that first letter, another letter, but now we have to have a 6, and we have to have a 6, and we have to have a 6, but now we're going to have letters again, 26, 26. So over the ways that we could have this exact same license plate, if we're not going to limit it to certain numbers, so there's going to be a lot of canceling on these 26. With fractions, if you see the same number in the numerator and the denominator with multiplication, those things are going to cancel. We can consider those gone. That's 1 over probability of getting that license plate given that situation. State's Department of Transportation plans to develop a new section of interstate highway, and they get 16 bids for the project. There are 3 bids that happen to be from companies owned by relatives of the governor. So we have 16 bids. There are 3 that are governor, using G for governor, and 13 N for not governor. How's that? Changing it up, keeping it fresh and exciting here. If the state plans to hire 4 of the bidding companies, What is the probability that all 4 selected happen to be owned by the relatives of the governors? Okay, will we put the bidding company back if we once we've selected them? No. So no replacement. The order does not matter. So this would be an NCR situation, a combination situation where we could do this. And so there were 16 non-governor bidders, and we only want one of those to show up. We want, of the 3 governor ones, we want all 3 to be picked. And on the denominator, the total number of ways we put everybody back together, 16, and we want to pick 4 companies to do this, put in their bids. So we get a probability of 0.001 or 714. You can think of it as, what if you went out there and picked 3 governor bids and a non-governor bid? There'd be 4 parentheses. I mean, this way of looking at it is just as effective, but the thing that makes this a little bit tricky is at this point, these aren't matching right now. That's because there were 4 ways this could happen. So when I multiply by 4, now I have the probability for finding that the 3 companies. So if this was random, if they were randomly selected and nobody even read the bids, that would be highly unusual to pick those 3 companies and then to have them take the jobs. Okay, we have 6 students running for the student council. There are 4 positions available: president, vice president, secretary, and treasurer. What's the probability of selecting those winning students and their positions in the order that we have there? No replacement. And the order matters. That's an NPR situation. And so we are going to find the probability of that happening. Probability, the 4 people with position, And so we could take, let's think through how many people were there. There were 6 people in all. There are 4 winners that, and their order would matter. And there are 2 that are non-winners. So if we have our 4 people, and the order's mattering, so we're going to have the order matter. But 2 of them, we don't want to pick any of them. And there's 6 in all for our total selections. This right here does become 1. There's only one way to pick nobody out of 2 people. So the probability of that happening is 0.00278. And these ones, examples like this with permutations, I really like to do them with the parentheses. I mean, it would be just as easy to set it up like this, to say there's only one person I can pick who's going to be the winner out of their 6 people in the room. Then now I got to pick the vice president out of those people in the room who are left, and pick that secretary. And now we're down to 3 people because we have no replacement. And that, I don't have to worry about the ways it got reordered like you do with combinations. So permutations I find are pretty easy to do just using parentheses. Okay, how is it different from picking 4 winners and not knowing their positions? Well, then we still have no replacement, but now order does not matter. We have an NCR for our 6 people, 4 being winners and 2 being non-winners. So I could go and do the same, any of the winners. And I want to pick out of the 4 that are there, I want to pick 4 of them. And and there's only going to be one way to do that. And then again, this is still going to 1 as well. There are 6, and we don't care about the order, so this automatically gets rid of those reorderings, and so that probability of that happening, yep. But if we were to do this using our system from before, we would have then had to say, well, how many ways could I have reordered 4 people? How many ways can you reorder 4 people? Well, there would have been 4 ways you could have picked the first person now that somebody's gone, and down until you've picked all 4 of your people. And so that would be 24 ways. And you'll see that if we took that 0.00248 and we multiplied it by 24 to get rid of those reorders, we actually would end up with what we got using our combinations formula. Okay, battery manufacturer. Sometimes we have to do a little work to figure out if a battery is, how many are bad, how many are good. Sometimes we have to do that. So we have 8% of the batteries in this situation are bad. So 8%, that's going to be 8 divided by 100, that's 0.08. So 0.08 times the number of batteries, we see that there are 80 bad batteries. So out of our 1,000 batteries, we have 80 bad. We have 920 that are good. That's a B right there. And we want to pick 5. So try to think about how you could do this with parentheses. How could you do this with combinations, because we have no order to this situation and we have no replacement. So we're going to be able to do this with an NCR. So I think I'll start with that probability that you, when you pick 5, that 2 are bad, then I got to pick 2 bad ones. So either it's 80 that I can pick from, I need 2 of them, but I need to pick 5. So out of the good ones, I need to pick 3 of them, and the total out there was 1,000, and you are picking 5 in all. So yeah, so that's going to be our answer. Let's see if we can get that with the parentheses. Same thing. So we've got our 5 parentheses for our 5 events that we're doing, picking batteries, and I've got to pick a bad one, if bad's what I'm doing first. And then now I've got to pick another bad one. But now I've got to go to a good one. So that's 920 good ones out of continuing my dependence and decreasing my denominator. So we get 0.0 4. It's just a little bit more boring with, well, actually, I guess this is boring normally, but, way more boring without any students. How many ways can we reorder our 2 bad and 3 good? Well, I'm going to use our distinguishable permutations, 5 items where 2 of them are the same and 3 of them are the same. And if you punch that in correctly, you find that there are 10 ways that you can do that. So let's multiply by 10. So let's see. Wait. Oh, I must have put there's supposed to be another 0 on this. So yeah, it comes out matching what we had up here. That was me forgetting to write one of the zeros. Okay, at least 1 bad battery. So if you want 5 batteries with at least 1 battery being bad, oh my goodness, there's going to be 2 to the 5th. There's going to be 32 ways to reorder this. 31 of them will have at least 1 bad battery. Only 1 way will be good, 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 good. There's going to be only 1. So when we're trying to find the probability of at least 1 bad, we're going to do 1 minus the probability all good. So let's do that. 1 minus, I need to get all good. So, well, the fastest way to do that would probably be to say, let's get our 920 batteries. Let's pick, without worrying about our order, let's pick 5 of them. And out of our 80 bad batteries, we don't want to pick any of them. So that's great. That goes to 1. Out of 1,000 batteries in all, where we're picking 5 of them. So, of course, I could always use my parentheses too, and I'd get 0.6. Luckily, no other ways to reorder this. So 1 minus the probability of being all good, because this was the probability all good. So we want 1 minus that, and we'll know at least 1 bad. So 0.658506. So the probability of getting at least 1 bad, 3, 4, 1. Yep. Well, do the last page. Probably if we were in class, if COVID-19 wasn't around, we probably wouldn't even get to this page, but I guess I'll do this for you now, just as a review. What if you want to find the probability of a person is happy given that she drinks Mountain Dew? So I don't know if that's possible, but happy, although when I was teaching a class on elections, Mountain Dew would frequently win our favorite drink for the class. So that's kind of funny. So a given statement, we're going to have happy and drinking Mountain Dew, but the given goes down below. Notice I have a P on both notations. I don't put the numbers from the table into my notation, but now I'm going to look for my happy people drinking Mountain Dew out of everybody, and my people drinking Mountain Dew right here. There are 52 of them still out of everybody, but those hundreds are going to cancel. So I get 10 out of 52, which is about 0.192. This is review, and that's why you have a review mini quiz to make sure that you can, because this is a different problem, happy and water, but it's different. It's not a conditional situation like above. You got to be able to distinguish the language, and so we're going to be looking out of the total, we want people who are happy and drinking water. So there are 3 of them out of the 100. And so that's in the last problem. I want the probability that you're sad or water. So this is our addition rule. We got to think about if we have, is there going to be overlap? Is this going to be a not mutually exclusive situation? It is, because you could be sad and drinking water. And so we have to have our probability of sad plus our probability of water. And we're going to take away the probability of sad and water. And so there are 60 people who are sad and 48 who are drinking water, but 25 of them are sad and drinking water. So probability of being sad or drinking water, 83 out of 100, so 0.83. Well, thanks for staying with me, and that was the last section for the unit, so make sure you're getting all your mini quizzes in, and I'll be watching in the Google Classroom.